Okay. Good morning. I'm very glad that you have endured so far and have come to my talk. The last talk of the DevOps this year, I really do hope it will be good, but let's see. So, the title of the talk is Where is my memory? And I will talk today about, well, memory leak. That's my favorite topic. So my name is Nikita Salnikov-Tarnovski. I'm from Estonian startup Plumber. Here is my details. If you want to follow me on Twitter, I will not talk today about Plumber. If you were interested, then you have come by our booth during the expo, so that's not interesting today. What will I talk today mostly? First of all, I will make a quick overview of Java memory management, just in case we have forgotten some basic details. I will talk about a little bit about how garbage collector does his work, what's reachability and why that is important in memory leak handling. I will briefly describe the different memory usage monitoring tools, and the main topic of this talk is in fact heap dumps and how to analyze them and why. Okay, JVM. When JVM runs, so JVM is just another process on your operation system. So JVM, it allocates memory from operation system like any other C process on the operation system, on the machine. And next, JVM divides that memory, that process memory, into different regions. You everybody knows that. We have heap with a different region, which more further on is divided into young generation, old generation, survival space, add-on space, etc., etc. And we have permanent generation. So different regions in memory, and on top of that you have native memory if you use some agents, or JVM uses native memory for its internal structures. That's all easy and clear. The default sizes of those regions, they are really dependent upon your computer, upon your machine, upon whether you run your JVM in 32-bit or in 40 or 64-bit mode. You can, if you just run your Java without specifying the XMX or XMN or any other memory-related parameter, JVM will allocate and divide those regions using some default that you can know if you're interested in using these options. And some people say that it may be a good idea to first run your application using just default provided by JVM without any manual tuning, because that may be enough for you. JVM is very, very clever, and it can handle memory very efficiently. It can tune memory very, very efficiently. So adaptive sizing, and which is turned on by default if you do not specify any manual parameters on your command line, it may be good enough for your application. So, and that is a general advice. Try to tune your garbage collector or your memory in JVM as little as possible, because when in my experience I have seen some command line parameters consisting of, or command lines consisting of 30 different parameters related to memory management and garbage collector, that's terrible, because I can bet my salary that nobody from that company really understands what every and each of that parameters really does. Copy-pasting different command line options from Stack Overflow is bad. Stack Overflow is very good, don't make me wrong, but copying without understanding what this specific parameter does, it's very wrong. Don't do that. Try to get away with as little parameters as possible. So, as a first step, just run your application with default sizes. They do depend upon total memory available for your computer, but try that first. Next, in the majority of cases, you really want to specify XMX because, well, by default, that's not big enough. Because the more memory you give to your JVM, in general, the more memory, the bigger XMX is, the faster your application will be. Garbage collector, in general, I generalize, in general, garbage collector work faster and better the more memory it has. The time of the garbage collector does not depend on the size of your heap. It does depend on the amount of live objects your memory has, or your application has, not on the size of the heap. So the bigger the heap, in general case, the better, until you start hitting the swap, and then you're in trouble. You're in big trouble. So two options, which is more or less the most commonly used options for JVM related to memory management, is XMX and, prior to Java 8, permanent generation size, or perm size. XMX is simple, everybody knows that. That's just the total amount of the heap. And on top of that, we have permanent generation. Default permanent generation size is, in fact, too small for the majority of applications. Permanent generation size is really one of the options that you almost always want to increase. And unless you're on Java 8, where you have metaspace, no permanent generation, and so you have every memory that your operation system can give you, more or less. Okay. Next, your JVM is running. You have some limits in place. Next, you as a Java developer is accustomed not to think about memory management. One of the selling points of the Java back, 20 years ago, was automatic memory management, which means that you do not need to write your mallocs and frees. You just allocate new object. You don't allocate objects, you create objects. You make new objects, and that's it. And you know that garbage collector will take care of that. And garbage collector is one of the most useful, or well, one of the reasons why JVM is so popular and so good. It's a subsystem of JVM which reclaims unused memory. And in Java applications, or in JVM, unused memory, in fact, in practice, means unused objects. Not unused memory per se, doesn't reclaim memory regions, some arbitrary memory regions. It reclaims objects. If object is not used anymore, and we will talk about that a little bit later, it will be thrown away. Garbage collector, let me remind you, is not JVM specific, and Java, in fact, wasn't the first to use automatic garbage collector algorithm. If I'm not mistaken, Smalltalk was earlier on this stage. And we have different algorithms regarding garbage collector, different runtimes. Use different algorithms for garbage collector, JavaScript, .NET, JVM. But if we talk about JVM, then differences in algorithms or differences between those algorithms mainly concern when to run garbage collection, when to collect your objects, not how to do that. From 10,000 meters perspective, every garbage collector algorithm on JVM do one and the same job. And that job is very strict and specific. Garbage collector tries to find objects which are not referenced anymore by other objects and throw them away. That's all. Every and one garbage collector algorithm on JVM, parallel, serial, CMS, J1, shenanigan, they all work on this principle. No reference, thus garbage. As simple as that. All differences between them concerns only when to run, and they mainly impact the performance from this point of view, how often and for how long garbage collector will run, not the underlying algorithm. And here we have to talk, that's really important in order to understand how garbage collector works, because in my experience, the majority of Java developers don't think about that, how exactly garbage collector work, what does memory leak means, and how that can happen at all in automatic memory management runtime like JVM. So first of all, we have to start with GC roots, garbage collector roots. Garbage collector roots are some special objects. Garbage collector handles them in some special way. They are special in that, and we consider, or garbage collector thinks, that those objects are alive always. Even if there is no reference in Java object sense that point to those objects. And GC roots usually, there are some of them, it's system classes, though classes loaded by bootstrap Classloader, so classes from rt.jar. We have JNI references from native code back to your Java objects, either from your own Java agents written in C or from JVM-specific structures in native memory back to heap. We have running threads that are still alive and running, so that object representing thread is considered to be reachable, or it's GC root. We have local variables and parameters. So whenever some method in your application is executing right now, all local variables from that method, which resides on the stack, on the execution stack, all input parameters for that method, they all considered to be alive. And garbage collector cannot throw them away. We have native stack, we have used monitor, so objects that you use to synchronize upon monitors. If some monitor or some lock is taken right now in this specific moment of time, it is considered to be alive, and garbage collector cannot throw it away, but by obvious reason. And some others, more or less obscure, but those are, well, the majority of GC roots are system classes, running threads, and local variables. So they are always alive. Next, we have a notion of reference. So in Java world or in JVM, you don't have pointers, at least in heap. You don't have direct pointers to some memory or to some address in memory unless you're playing it unsafe. You have references. In JVM, you have different types of references. Some of them are on this slide. So the most common one is you have object, you have fields in those objects. So you have reference from objects to its instance field. That's simple, the most common reference from one object to another. You have references from array to its elements, simple. You have a reference from every object to the class of that object. You know that class is, well, just another object of the type Java-lang class, so you always have reference from object to its class, and that is important. The existence of that reference is important. You have reference from a class to its class loader. So every class has a reference to the class loader that has been used for loading that class. And the existence of this reference is also very important at the end of our talk. Okay, you have reference from a class to its static fields. That's easy. You have references from class to its superclass. So we have GC root. Whenever garbage collector kicks in and starts hunting for garbage to throw away and to reclaim some more memory, first of all, it marks all GC roots as reachable. I simplify a little bit because, well, the real GC algorithm is a little bit more complicated, but that's good enough for us today. So we mark all GC roots as reachable. Then we follow references from reachable objects. We follow all references from reachable objects to some other objects, these references. And we mark those objects as reachable too. And repeat, rinse and repeat. So we repeat this process by process of walking the object graph until we mark all objects which are transitively reachable from GC roots as reachable. And these objects are alive. They are in use by your application, or they are considered to be in use by your application or by JVM. All other objects, all objects which is left unmarked, they are garbage and they can be thrown away. Garbage collector will throw those objects away. It's as simple as that. Very simple algorithm, very powerful algorithm, but very simple. That's why the time of garbage collector, the performance of garbage collector, is proportional to the amount of your leaf objects, not to the size of your heap. Collecting garbage per se is free of charge. Deciding which objects are alive, that takes time. Okay. And so what is a memory leak? How can memory leak happen in JVM, in managed memory, in managed memory runtime? Memory leak definition in JVM on Java application is quite different from those of C application. In Java, we have a memory leak when we have reachable objects, reachable by previous slide definition, but those objects will not be used by your application anymore. So that's not a technical definition, that's business definition. That's your application-specific definition. It totally depends upon your application, business rules, and algorithm if some object is leaked or not. Will it be used by your application in the future or not? And from the practical point of view, memory leak becomes a problem when you have repetitive creation of such objects. When during runtime of your application you create objects, you put them somewhere in your application, they are reachable, they have incoming references, so garbage collector cannot throw them away, but your application will not use them anymore. you forget about them, and then you have a memory leak from the practical point of view. Examples of memory leaks are very simple. If you have cache, but you forget to use that, you put something into cache-like structure, but you do not look it up, you have a memory leak. In older versions of Java, in previous versions of JDK, you have a memory leak. You can have a memory leak when you use substring, for example. If you have a huge string, if you have a long string, and you call substring, in previous versions of Java, in Java 6 and in earlier versions of Java 7, if I'm not mistaken, when you make substring just takes that char array, which is backing that string, and just says, okay, I am now pointing to some window in that char array. And that's it, that's substring. And the whole char array, which is not reachable anymore, is still in memory and cannot be garbage collector, and you have a memory leak. If your application or in some library in your application starts a thread and forgets to kill that thread, and that thread monitors something, it looks for something, so it's always alive, it has some while true or wait inside it. It's memory leak because you cannot use that thread anymore. Unclosed input-output streams and some other. So you can have memory leaks in your application. And there are lots of them. I have another talk about Classloader leaks when I demonstrate that every and one, or almost every and one, web application in Java, in fact, has at least one memory leak. Okay, why memory leak is a problem? Because when you have memory leak and you have that constrained memory, every Java process, every running JVM has constrained amount of memory, constrained either by XMX amount or by default value. When you use that memory up, you will get out of memory error and your application will crash. Out of memory is usually unrecoverable and your JVM will crash. Or your application will be damn slow because most of the time garbage collector will try to free some memory, but if you have memory leak, memory is used, garbage collector cannot throw those objects away, and you have repetitive and constant GC running, and you have no CPU cycles left for running your application, and well, your users will be unhappy. But those symptoms doesn't tell you that you really have a memory leak. That's only one of the possibilities. Another one is you just allocate too many objects too fast. And GC in your memory amount, in your heap size, you just cannot handle so much garbage so fast because it runs too fast. It's a very usual situation. It's a very big problem for some low latency environment. For example, in financial trading, they monitor the allocation rates very closely, because that can be a problem, but that's not a memory leak. That's garbage. It will be thrown away, but it's just too much garbage. If you have cache with wrong size, too large size, you use that cache. You constantly look up objects from that cache, but that cache is just too big to fit into your heap alongside other objects that generated during your application runtime. You will have problems. You will have a high GC rate, and you maybe even you will have out of memory, but that's not a memory leak. That's a configuration problem. Sometimes, when you just try to load too much data at once, for example, from your persistent storage, you will get out of memory, but that is not a memory leak. Because if you had much more memory, you load those data, you handle that, you process that, and you are done. Garbage collector will handle that, it will throw them away, but you try to squeeze an elephant into a shoebox. Just not enough space here. And fat data structures. I very like that example, that for example, Java util hash set. Very common data structure. Everybody uses that from time to time. But on average, when you measure how big hash set is, how much memory it requires to hold particular amount of data, of raw data in it. On average, Java util hash set has overhead of 13 times. In order to put, for example, 10 megabytes of raw data, of raw integers, for example, into hash set, you require 13 times more memory. So hash set will be around 130 megabytes of memory. So fat data structure can be a real big problem. But again, that's not a memory leak. Memory leak is only one of the possibilities why do you have out-of-memory errors or high GC rate. So how can you make sure if you have a memory leak or what's going on inside your application? Your administrators report back to you that your application has crashed with out-of-memory error or that it's too slow. What can you do? So essentially, you have at least two different tools that you can use to monitor what's going on inside your JVM, what's going on inside your application regarding memory consumption. And one of them is Java Mission Control or JConsole. Close that, so close. So you just monitor your memory like that, or why it's not moving? Okay, doesn't matter. And another tool that you can use on your production system is JSTAT. Like that. Okay, so first of all, every JVM application should be monitored for what's going on inside it in order to spot problems early on. So you can monitor your memory. Why that's not show last hour. Okay, that's better. Show last 10 minutes. That's even more better. So if you see something like that, if you see that your used memory constantly rise, okay, it's a good guess that you have a memory leak. If your application runs smoothly, more or less constantly, and sometimes and right before your crash you have huge spike, then maybe that's not a memory leak. Maybe that's trying to squeeze elephant into shoebox. You just try to load too much data from your persistent storage, for example. If you see that your GC graph is constantly oscillating on top of your heap, so that's a good guess that you just try to allocate too to allocate too much objects, and your garbage collector constantly throws them away, and you create them again, it throws them away, and so on and so forth. But that's not very interesting, and one important thing is GC logs. Garbage collector logs is very useful tool for analyzing what's going on inside your application regarding memory consumption. You can switch them on using these options for your command line. And my advice to you, in every production environment, for every JVM that you run, turn them on. Garbage collector logs are free of charge. They do not provide any overhead on your running JVM, and they are the most useful tools for analyzing your memory performance issues. Okay, not your JVMs. Turn them on always. Garbage collector logs are essentially where are they? Where are my logs? GC logs get. Where are they? Okay. Essentially, it's a text file where JVM prints every GC event that happens during JVM runtime. Reading GC logs just by reading that raw file is really painful, and sometimes as well it's too much data, and so do not do that. Use some GC logs analyzers. There are plenty of commercials and open source GC logs analyzers, and I use GC Viewer, the last one. For me, it's pretty good. So GC logs should be turned on always, and they give you the opportunity to get a nice visual representation of what was going on inside your application in the past. I mean, so if you have that. If administrators or your operation guys told you that your application is done slow or it has crashed in production, then you have very little data about what was going on inside that JVM before it has crashed or before it turned so slow. And GC logs visualizers can give you pretty good estimate. Like here we see that we have constantly increasing memory consumption. So it's pretty good guess that you have a memory leak. And when you look at GC activity, that you see, okay, my application is slow because GC is constantly running. GC log analyzers and GC log analyzing is sometimes black magic, because to tune GC based on logs, it's very complicated beyond some point. But if you have low-hanging fruits, that like in this case, you see what's the problem. It's very easy to spot here. Okay, what can you do after that? So you have confirmed You look at your GC logs, you have looked in your memory consumption, and okay, yes, I see what my problem is. Is that spike? Is that a memory leak or what? So you can try to reduce memory usage. You can change your algorithms. You can change your data structures. You can tune your GC so it would run more often, or you can tune your XMX. Sometimes just increasing available heap is the right thing to do. Sometimes. But for example, if we have concluded that we have a memory leak, what to do? The best way to solve memory leak, well, the best way is, of course, is to use some specialized tool I have promised not to talk today about. But the second best way to solve your memory leaks is to take a memory dump. Memory dump is just a binary representation of the heap. We take a running JVM, we take that heap, that memory region, and we dump that into file. It's not one-to-one a binary dump. It's binary representation of object graph in memory. Well, object graph in memory, binary representation on the disk. It's not accurate representation of what was in the heap at the time of the memory dump was taken. Heap dump loses a lot of information, a lot of runtime information about your objects. For example, individual object sizes are almost always wrong in, more or less wrong in heap dump. Object layout is totally lost. It's not accurate representation of the heap, but it's good enough for memory leak detection. So how can you take memory dump? Two ways. The first way, if your JVM is still running, you can use JMap tool, which is part of the JDK, and dump that into file. Please note that memory dump creation, or heap dump creation, that stop the vault operation, which means that during heap dump creation, the whole application is stalled. It doesn't do anything. All threads are stopped. So for your clients, your application is unresponsive. So do not do that very often, please. So prophylactic memory dump creation every 5 minutes is bad idea. The other option how to get a heap dump is to add one more parameter to your command line, heap dump on out of memory error. And in this case, whenever your JVM throws out of memory error, it will create a heap dump. And again, that's the second option that should always be on in your production system. Every production environment and every production JVM has to have this option, heap dump on out of memory. Because when to get a heap dump or a memory dump? That's a very good question. Because imagine the situation, your operation guys report to you, we have application crashed with out of memory error. What should I do? You say, okay, next time I need a memory dump from that application. Okay, operation guy, start your application again, then immediately takes a memory dump and send that to you. Look for memory leak. Is this a good idea? No. You should get memory, when you hunt for memory leak, you need memory dump as late as possible. When that memory leak in your application has grown enough to be easily spotted in that heap. And that's why heap dump on out of memory is the best time to take heap dump. Because that's the time when your heap is the biggest. So it should always be on. Okay, you get that huge file because the size of that memory dump is more or less equivalent to the size of your heap. So if you have a heap 60 gigabytes, you will have a memory dump for around 60 gigabytes. So now you should get that heap dump from your production environment to your developer machine. Next step is to add more RAM to that machine, because you need more or less, in general, almost the same amount of memory for parsing that heap dump, or that parsing will take a really long time. And then you download active memory analyzer tool called MAT, Memory Analyzer Tool, and it's the best tool on the market so far to analyze heap dumps, in my opinion. But before I switch to memory analyzer tool, we should speak about size of the objects. So when you have a memory leak in your application, you want to open that heap dump, and if you are lucky, then you should search for biggest object in that heap, or the object that consumes the biggest amount of memory. But what does this big mean? What does object size mean? That's a good question, because when we talk about objects and size and object graphs and memory and heaps and heap, we have at least 3 different sizes of objects that we can talk about. First of all, we have shallow size of the object. Then we have a deep size of the subgraph, which starts from that object. And I will make an example in the next slide. And then we have a retained size of the object, or the size of the subgraph which is dominated by that object. And in this slide, domination is a good word, it's not a bad word. So, when we have shallow size, the shallow size of the object is the size of that object with its headers and its fields, but without the objects that live in those fields. Because, well, every field or every reference in JVM, it's a pointer, so it's 4 bytes, well, not a pointer, it is a reference, so it's either 4 bytes or 8 bytes. And so the more fields object has, the bigger that object will be in memory. Okay? That shallow object size, the size of one object without objects referenced by its field. Header, object, and its field. Then we have retain size and deep size. So deep size of the object, if we have object, in the memory we have graph or subgraph, which starts from that object. We have object which references other objects, who reference other objects, and so forth and so far. So the deep size, for example, of object O1 on the slide is the size of all subgraphs, the sum of shallow sizes of all objects in the subgraph. So O1, or 2, or 3, or 4. Retained size of the object is the size of the subgraph that could be garbage collected if that object is thrown away. So if we throw away O2, for example, so garbage collector decided that O2 is garbage and throws that away, then nothing else happens. We still cannot throw away O3 or O4 if O1 is our GC root, because O3 is still referenced by O1. So the retained size of O2 object is just the shallow size of O2. But if you throw away O3 by breaking those references from O2 and O1, then O4 will be unreachable too. So the retained size of O3 is the sum of the shallow sizes of O3 and O4. Why is this important? Because when you open your heap dump in memory analyzer, then it will show you the objects with the biggest retained sizes. And usually they are those objects that you hunt for. Usually when you hunt for memory leak and heap dump, you look for objects with the biggest retained size. Because if you can understand why those objects are still in memory, why they are not garbage collected, and you solve that problem, assuming that those objects are really not needed anymore, then you will reclaim the biggest amount of memory from your heap. So that's the biggest win if you throw that retained size, that retained object. So in this particular case, we have a representation of the heap, and we see that the majority of the heap is accumulated or belong to the subgraph dominated by one particular object below its leaking interceptor. Okay, leaking interceptor, easy, that should be our memory leak. And so what would you do? Now your task is to understand why this object is still in memory. So you have to, well, in fact, you have two tasks. First, you have to understand why this object is so big. Second, you have to understand why it's still in memory and not garbage collected. So what you do, in order to understand why this object is so big, you click here and you list objects with outgoing references. So you just ask memory analyzer, show me that object and the whole subgraph from that object. Which objects are referenced by that object, transitively, and so forth and so far. And so in this particular case, we see that we have some linked list which has accumulated some image entries. Okay, more or less, you can understand this way why this object is big, why it's in memory. That's the second question. And that's easy. You click on this object and you now try to find some paths or some chain of references from GC root to this object. You want to find out why garbage collector has not thrown that object away, because there is some chain of references from some GC root to this object. Now you want to find that chain, where in memory this object resides. And so you ask path to GC root, excluding all phantom, weak, soft, etc. reference, and well, if you do know why you exclude, good. If not, that's unfortunately I haven't enough time to explain. And what we what we see here, we have our object. Unfortunately, Math UI don't allow me to increase the font. So we have leaking interceptor object, which is our leak. This object is referenced by leaking interceptor class. So we have some static reference. That leaking interceptor is referenced by some Spring handlers, and it is referenced by Classloader. In this particular case, it's easy. So we know that we have an object of type leaking interceptor, which resides just in static field of leaking interceptor class. So in this particular case, it's very easy. We open leaking interceptor class, we see that static reference, and now, knowing your application business rules, you can decide why I put those objects in these objects and why its static reference is, well, it's immortal. Because in order to solve memory leak, you have to answer the following questions. What takes so much memory? And we know who takes so much memory. Why it's so big? So we look what lives inside that object, where the majority of objects live. Why it's still in memory? You have to find the paths to GC roots, and to decide, and you have to break those paths in some way. In this particular case, as we see that we have some collection of objects that grows and grows and grows, so you have to break reference between your collection and objects inside. You have to throw objects from that collection. And you have to, and then you have to understand how to solve that. The last question is not technical anymore. It's your business application decision. How to change my application so those objects are not accumulated anymore in this container or in this object. First questions are technical ones. Last question is business one or application specific one. So, very easy. You take a heap dump in right moment. You transfer that multi-gigabyte file to your machine. You add more memory to your machine. You parse that object from using MUD. You hope that you get such picture, because in some cases you get this picture. So you have no single winner who takes so much memory. You have no single object. Then you can try to ask memory analyzer, show me who the suspect, why I have a memory leak. Sometimes those reports are useful, sometimes not. Okay, here we socket implementation. Sun Security SSL socket implementation. Do I have problems with Sun sockets, or do I have some problems with finalizers? That's the case, that's the place, in fact. If you are not lucky, if you don't have such a picture, you have such a picture, then the only thing that can save you is experience, in fact. That's one of the biggest problems with memory dump analyzers. If you know how to do that, it's really simple, because I do know why that and how to solve that and how to understand that, because sometimes in the past, about 6 or 7 years ago, I have spent 6 hours trying to decipher what does this means. If you don't have experience, you can ask Eclipse Analyzer, show me this, and then you ask Google Java Lang Ref Finalizer memory leak, and hope that you will be redirected to our blog when we describe this particular problem, or to Stack Overflow where somebody has solved this problem. If not, sorry. Yeah, so you pray that you are lucky, that you get that picture. If not, well, you try to Google and Stack Overflow. It's interesting that there is no such verb so far, Stack Overflow. You have verb to Google, but not to Stack Overflow. Okay, strange. And okay, and I have a little bit time, so one specific type of memory leak or specific class of memory leaks in Java applications, especially in web applications, is Classloader leak. And Classloader leak is a little bit different from usual heap leaks, because when you have your web application running in your application server and your web container, Tomcat, Wildfly, Jetty, or WebLogic, or WebSphere, and your application is undeployed for some reason, or redeployed. So your application is undeployed or stopped for some reason. But you have some bug in your application on your library, and you have left one object from your application somewhere referenced by application container. It may be thread running. It may be some objects published into JNDI tree, for example. If you have left one object from your application behind your application, that object, as I have told already, will reference its class, and class will reference its class loader. And in hotspot implementation, or let me tell, in Oracle, in OpenJDK and in Oracle JDK, we have class loader referencing every and all classes that has been loaded by that class loader. So if you have one object, it will reference class, it will reference class loader, it will reference every and one classes from your web application, from your web in flip folder. So all classes will be in memory in your permanent generation or in metaspace. So you have to find that one object which has been left behind your application, one object or more objects if you are not lucky, and break that reference from GC root. And how you do that? In this case, Eclipse Memory Analyzer is perfect. It's really easy to find class loader leaks with Eclipse Memory Analyzer. What you do, you open your heap dump again, and you click, if you see duplicate classes link. And it will show you every classes from your application that has been loaded by more than one class loader. And in situation when you have your application running and you redeploy your application with new version, you have classes from your WebInf flip or your WebInf classes loaded by a previous application, which is still in memory because we have a leak. And the same objects will be loaded by the new copy of application. And so here we have objects, or we have classes loaded by two class loaders. One of them is legit class loader of the new application. So it's good and it should be there. The other one is leftover from your previous one. And when you ask, give me paths to GC roots from this class, in one case you have several paths, like in this case. In other case you have only one. So the second, the one with the smaller amount of paths, is leftover from your previous copy of application. In this particular case, you see that you have a chain of reference to that web app class loader, and the beginning of that chain is in Java SQL Driver Manager. And now you just Stack Overflow Java SQL Driver Manager class loader leak, or Google, and then it will show you our blog when we explain the problem, or Stack Overflow. So that's easy part, really. You find that that culprit, and you Google that, and in the majority of the cases, you will get your answer. Class loader leak detection is easy. Now, how to solve that may be a problem because sometimes it's library problem, and you have no control on that. Okay, what about other tools? And I really beg you, do not use profilers to solve your memory leak. Because sometimes when you Google how to solve memory leak, and there are many answers about profilers, do not use them. Sorry to disappoint you, but Java profilers, Yokit, JProfiler, what you name it, they're not good tools to solve memory leaks. I know only two tools that can solve memory leaks. One of them is that we cannot name today, and the other one is Eclipse Memory Analyzer, if you can use it or if you are lucky. And that was all for my presentation today. Thank you for your attention. If you have any question, you can grab me. I'm here for some time. And please do not forget to vote if you like that presentation. Thank you.
Performances in 24 faces, Benadorm Vegas, many more praises. Amen, hallelujah, tiny little